Hello, welcome if this is your first time joining us, and welcome back if you already joined us at least once. Feel free to check our other videos. And in this session, we are going to talk about prime factorizations and GCF. And GCF stands for Great Common Factors. In our previous session, we spoke about the term cancellation and the term lowest term and also the term common factor. So we know what they all mean. And here we can say that factorization of a fraction is the reduction of that fraction to its lower or lowest term. And to be able to reduce a fraction to lowest term, we must identify and use a common factor greater than 1 of the numerator and the denominator. So recall that for now we are just dealing with positive numbers. We can reduce a fraction in many steps, but if we don't want to go through many steps, what we have to do is we must find and use the largest common factor that we call GCF, right? Which means the greatest common factor. For everything we said until now, we have an idea of what is GCF and what is factorization. Now, what is the word primes mean? A prime number is a whole number greater than 1 that has no factor other than itself and 1. I'm going to repeat again. A prime number is a whole number greater than 1 and that has no factors other than itself and 1. Meaning if we take a number and divide it by another number different from 1 and different from itself, if I get a result with a remainder equals 0, that means that the original number is not a prime number. We should not be able to divide a prime number by any other number except 1, number 1 I mean 1 and itself, and have 0 as remaining, right? So prime numbers are, we can just cite them: 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, and more. We have more. There are more and infinitely many of them that are prime numbers. So let's open a parenthesis and say that all other numbers that are whole numbers greater than 1 that are not prime numbers are called composite numbers. So prime numbers, these are prime numbers. So opposite of prime number, the opposite is called composite number. And some example of composite numbers are 4, 6, 8, 9, 10, 12, 14, 15, 16, 18, 20, and we still have more. Each of these composite numbers, has at least one factor other than the number 1 and itself. So you should have realized that from composite numbers and from prime numbers, we don't see anywhere the number 1, right? So 1 is not part of prime numbers. 1 is not prime of composites. So 1 is special. 1 is special. 1 is not part of prime numbers. 1 is not part of composite numbers. So 1 is just special and is by itself. So let's close this parenthesis right here and back to prime factorizations. How do we find prime factorizations? We take our number and we start dividing it by prime numbers. So we start by dividing by 2 because 2 is the smallest positive prime number. If our number is divisible by 2, we divide by 2 and the result of our division becomes the new quotient and we repeat the division by 2 as many times as possible. Once we cannot divide by 2 and if the result is not a prime number, then we try dividing with the next larger prime number. If possible, we divide as many times by that prime. Once done with the actual prime number, we repeat the process again, if possible, with the next larger prime until we reach a point where the result or the new quotient is a prime number itself. Then we stop. It's not finished yet. So what is next? If we haven't finished, we collect all the primes that were used as divisor with the final prime or the final quotient or result. Now the product of this or that collection is the prime factorization. Hmm. I know I spoke a lot and maybe so far nothing makes sense. Don't worry, pause the video, listen to the same thing and many times and we will continue with example. Let's do our first example and the question will be example 1, right? Find find the prime factorization of 100. Find the prime factorization of 100. So based off all we said previously, we take our original number, which is 100, and we start dividing it. Which one is the first prime number that we can use? 2, right? We divide by 2. What is our result? 100 divided by 2, we have 50. So is 50 a prime number? No. Then, because 50 is not a prime number, 50 will be our new quotient that we will use. And we come back and we will write 50. And we divide again by the first prime number, which is 2. Can we divide? Yes. What is the result? 25. Is 25 a prime number? No. So we come back, we write 25. What is the first prime number we can divide by 25 with? Let's try 2. 25 divided by 2. Do we have any whole number as a result? No. So let's move to the following greatest prime number, which is 3. Let's divide 25 by 3. 25 divided by 3. Do we have a whole number as a result? No. Then we keep trying. We go to the following larger prime number, which is 5. Can we divide 25 by 5? Yes. 25 divided by 5 equal to 5. Okay. Is 5 a prime number? Yes. So we stop there. And now, as we said, we combine all the prime numbers that we have used in our steps, include the final result, which is the final quotient. So if I will highlight them, They are these numbers. Include my final result. I will have 2, 2, 5, and 5. If I want to label them, I'll say this 2 is right there, this 2 is right there, this 5 is right there, and this 5 is right there. So what is next to do? The product of all of them, right? So we do my prime factorization of 100 equal 2 times 2 times 5 times 5. So these are my results. And I stop there. You don't proceed. You don't find, you don't just multiply and give back the result. If you start multiplying this, you will end up having 100. So what you need to give as a result is this one, that we can better write it. How do we write it? How many times we have 2 there? 2. This is equal to 2 to the second times 5 to the second, because we have 5 multiplying itself twice and 2 multiplying itself twice. So this is a better approach if you don't want to just write them straight like that. Let's do another example. And here, find same thing, the prime factorization of 300. Let's start. We write our 300. We divide by the smallest prime number if possible, which is 2. Can we? Yes. The result is 150. Is a 150 a prime number? No. So we come back, we write 150. We divide by 2 if possible. Can we divide 150 by 2? Yes. What is the result? 75. Is a 75 a prime number? No. So we come back, we write it 75. We divide by what? We try to divide by 2. Can we divide 75 by 2 and have a whole number? No. So what do? We move to the next larger prime number, greater than 2 that we are using. And that's 3. Can we divide 75 by 3? The result is yes. So let's do it. The 75 divided by 3, we have 25. Is 25 a prime number? No. So we keep dividing, right? So we write 25. And here, what are we using? Can we divide 25 by 2? No. Can we divide by 3? No. Can we divide by which one is the next prime number after 3? That's 5, right? Can we divide by 5? Yes. 25 divided by 5 is 5. Is our result 5 a prime number? Yes. Since our final result is a prime number, we stop there. And we come back. And our result 300 is equal to, as we said before, we just write the product of the prime numbers that we use and the final result. We have 2, 2, 3, 5, and 5. And then we just put a dot or a multiplication sign in between them. So we can stop here, or if we want to fancily write it, we have 2, 1, 2, 2. So that's 2 to the second power times, how many times do we have 3? 1 time. So 3 1 times 5. How many times do we have 5 here? 1, 2. We put 2 there. So this is our result. This is our prime factorization of 300. Before we continue, do this. You find the prime factorization of 35. What is your answer? If after trying you find 7 times 5, then you are right. Otherwise, you may try again, or if you don't know how to proceed, just mm, express yourself in the comment section, and we will try to redo it together. Let's now move to finding the GCF. So first of all, we found the prime factorization. Now let's try to find the GCF, which is what? Greatest common factor. So we find a GCF on a set of numbers, and using prime factorization makes it easy. That's why we saw first how to find our prime factorization. So now the prime factorization that we found, we are going to use it to find GCF. And to find a GCF, there is a set of steps to follow. And these are the steps. Number one, find the prime factorization of each number, right? Number two, determine the prime factors that are common to all the numbers. Number three, if there are no prime factor common to all the numbers, then the GCF is 1. So if there are no common prime factor to all the numbers, then the GCF is 1. And if there are common prime factor, then we go to number 4. And at number 4, for each common prime factor, we find the small exponent that appear on it. So for each common prime factor, we find the smallest exponent that appears on it. Then we move to number 5. And at number 5, the GCF is the product of the common primes factor with the exponent found in the step 4, like a previous step. So the GCF is the product, right, of the common prime factors with the exponent found in the previous step or step 4. I mean step 4 that if this is if you are following how we listed our steps. And we can call this a formula, right? Say how to find our GCF, and we can call it a formula. Let's do an example. And we said that a GCF is found on a set of numbers. So in our example, we will find the GCF of the set 60 and 135. We are going to follow the steps that we listed seconds ago. So first, we are going to find the prime factorization for each number. So for 60, the prime factorization is 2 times 2 times 3 times 5. Or we can just write it as 2 to the second power times 3 times 5. And for 135, the prime factorization is 3 times 3 times 3 times 5, or 3 to the third power times 5. Okay, so the next step says to determine the prime factorization that are common to all the numbers. And here, the, from our result, we only see 3 and 5 as common prime factors. If I take this part and I put it here, I have 2 second times 3 times 5. And I have 3 and I have 5. So we have 3 and we have 5. So there is no 2 for 135. So after this step, we go to step 3. If there are no prime factors common to all the number, then the GCF equal 1, right? But in this case, there is a common prime factor. So what we do is for each common prime factor, we find the smallest exponent that appear on it. So this is step 4, each common prime factor. So for 3, when we look at our results for 60, the 3 has exponent 1. And for 135, the 3 has exponent 3. So the smallest exponent for 3 is 1. So smallest exponent on 3 equal 1. And if we take our 5, the smallest exponent on 5 equal what? 1. 1 plus on 1, when on a number you don't see any exponent, that means 1, right? So it's 1. And finally, in the step 5, the GCF is 3 to its lowest exponent, which is 1, right? Times 5 to its lowest exponent, which is 1. So when the exponent is 1, we just write it simply as 3 times 5, and our result is 15. I know this is a little bit too much, but just review the video as many times as you can, and then you will get it better. And if any question, as I always say, ask in the comment. So we are going to finish, but before we finish, let's talk about one more point, which is cancellation or canceling the GCF for lowest term. So canceling the GCF for lowest terms. We are going to use our set 60 and 135 that we used before. And we know that the GCF, the GCF of our 6135 is equal to 15, right? We just saw it. So if we want to reduce the fraction, for instance, 60 over 135, using these two numbers as a fraction, we will just cancel the GCF, right? So we will have 4 over 9. So I just gave the result. How do I get to the result? So we said we will cancel the GCF. So exactly what we did was divide 60 by our GCF, which is 15, over 135, divide for our GCF, which is 15. We use the same GCF. And if we divide 60 by 15, we will have 4. And if we divide 135 by 15, we will have 9. And this one, we cannot reduce it. There is no other number that will go into both. And that's the same number that will go into both. We only reduce if we have the same number that goes into top and bottom. So that's what we call canceling the GCF for lowest term. So as long as we have a final fraction that we cannot reduce, we call it lowest term. Okay. So I think for this confusing topic and long video, we should stop here and continue next time. Any question, please don't be discouraged. We did talk a lot, and it wasn't as clear as you wish it should be. I advise you to review the video, and as I said, anything, just leave your comments, and we may come back with more example in one of our next videos. So for now, take care, and I see you in the next video with another topic. Bye for now.